Okay, let's continue. And the next topic we want to talk about is how efficient the Kruskal algorithm is. Okay, well, and by the way, Kruskal algorithm is the second MST algorithm we are going to cover. Well, when I learned the MST when I was in college, and I find that Kruskal algorithm is much easier than Prim's algorithm. Probably you feel the same way as well. Okay, so what are the things, what are the components that a Kruskal algorithm have? So the first one is I see a sorting, right? So on line 4, there's a sorting, and we are sorting a total of E edges. And after that, for the line 2 and 3, and we have a make set for each of the nodes. So we have a total of V make set calls. And the next part is when we have a pair of the U and V, and then we want to call the find set of the U and the find set of the V. So we are calling the find set U and V each time we see an edge. So we are going to do a OE find set calls, and eventually, we may union. Uh, our goal is that we are going to union all the nodes together, right? We are going to union all the nodes together into one big set. So in this case, we are going to do a OV union calls. So the sort, we know that is a n log n, and then for the make set, find set, and the union, our next question will be those three function calls. How computational expensive are they? Okay, so that's the summary, and we are sorting the edges, so that is the E log E, and then we have the OV make set, OE find set, and then OV a union. Okay, so if we somehow can prove that this one is the most significant term, and then this Kruskal algorithm will be OE log E. And can we really prove that? And then we have to go back and talk about how we can implement a disjoint set. Okay, so this is a easy idea, and we just want to use a linked list. Okay, so we have one node, another node, and then we just link them together into a linked list. And one tricky thing is for each of them, and they have a back reference to their head. Okay, so let me bring up my pen. Well, so we know that this is a head. And then say for the node A, node B, and node X, they are in the same set. And then when we are trying to get to do a find set, and then it will just we will use the back reference to the head, and then in the head we can have a unique identifier again. So for example, we can say this is a set 1, or we can say this is the red set. It doesn't matter. So if we have the B, for example, and then I want to do a find set, and then I'm going to take this back reference to the head, and in the head we have either the set 1, which is the name, or we have a color, which is red. So in this case, to do a make set, the make set is definitely a constant time because we are just adding one node to a linked list. Okay, and then for the find set, it is also the constant time because we only need to take a back reference from A to the head, and then we only need to read the information in the head, and then we can tell what is the unique identifier of a set. Okay, and then the next part, how about the union? So we know a make set is a constant time, and then the find set is constant time. And the next part is the union. When we want to combine the set A and set B together, how do we do that? And the easiest way is, how about we just copy all the nodes from the set A into set B. Okay, so say we have A, B, and X, and then we have uh, Y and W, for example. Say this is the set A, this is the set B. And then when we are trying to do a union of the set A and the set B, and what we will do is we will just move the A and then the B and then the X into the set. And then of course we are going to add the back references. So A will refer to the head, B will refer to the head, and then X will refer to the head as well. So in this case, this is how we can do the unit. Okay, so if we want to analyze the unit, well, and then if we start from S1 and S2, and then if we start from the very beginning S1 and S2, they both have one item. Okay, so this copy, we will copy one item. And then if we want to union S2 and S3, and remember in this case, S2 has already got two items. So in this case, we are moving two items. And eventually, if we are unioning the Sn minus 1 to Sn, and then we are copying a total of n minus 1 items. So in this case, well, in the worst case, we are going to do a total of O(n) square copies. Well, O(n) square, that's not cool, right? So remember we say if we, among those four terms, if we find that OE log E is the most significant one, and then the Kruskal is OE log E algorithm. And then if we want to do OV units, and then that will be OV square algorithm. So it's not so cool. So now O(n) square, it's really too high. And the next topic will be how can we make the union a little bit faster. And the idea is instead of always copying the first set to the second set, now we want to do a comparison. So when we are unioning the S1 and S2, I want to do a comparison, and I'm copying the smaller set. I'm copying the smaller set into the larger set. So this will save me some of the time. Okay, so well, in this case, well, this will take O(n) log n time. So this n square time will be improved to the O(n) log n time. And what is the n? The n is the number of the vertices, right? So this will be OV log V. Okay, so how can we do that? And this is a new trick of analyzing the time complexity, and it is called amortized analysis. Well, and we can consider this way. Well, if we only copy the smaller set into the larger set, and then if we just consider one atom, and then this, if the first time this item is copied, and then this item is copied to a destination set which has at least two items, right? So we are copying a set to another set. So if we are moving this set, and then I'm moving this item to a larger set. So in this case, well, after the first copying, and then this item is in a set with at least two items. So how about this this item is copied again? Well, if this item is copied again, and then we are copying that to a even larger set, so the destination set has to have at least four items. So if we just copying that again and again, so eventually the log nth time we copy this item to a larger set, and then the size of the set has to be greater or equal to n. So that is the upper bound of how many times an item in a set can be copied. And the strategy is we always want to copy a smaller set into a bigger set, and then the upper bound that an item is going to be copied will be log n. Okay, so in this case, well, if we go back to this part, we have those are the four components of the Kruskal algorithm. So the first one is O E log E, and then we don't have to do any changes. So we are just gonna say, okay, that is O E log E for sure. And then we have the OV, and then OV multiplied by the make set, and then the make set is a constant time. And then the next one is OE. OE multiplied by the time complexity of the find set, which is another O1. And finally, if we do a total of V units, and then that will be O V log V. Okay, so those are the four components of the Kruskal algorithm. And if we just want to add them together, and then we want to pick the most significant part, which one should we pick? Okay, so we definitely don't want to pick this one and this one. Okay, so the next question will be OE log E and the OV log V. Which one is higher? Are we going to have more edges, or we are going to have more vertex? So usually we have more edges, right? So this one will be the most significant part. So that's the reason we are saying that for the Kruskal algorithm, that is a OE log E algorithm. Okay, so and the next thing is we want to come back. So for a total of n units, a total of n units, and the time complexity is n log n, right? So if we want to say what is the cost of one unit, the cost of one unit is a log n. Does that make sense to you? That's weird, right? So when we are doing one unit, at least we are moving one item to another set. So it sounds to me like that is a constant time. That is O1. But for a O log, why it is a O log n? Well, because we are doing a this is similar to a amortized process. So at the beginning, we are paying a price, and however, the first price multiplied by n is not the total price you pay. Okay, so you're paying a down payment for each of the small part, and then as the time move on, and then we are paying more and more and more, and then at the very end, after we have already paid off of this loan, and then you use the total cost of this loan, which is a O n log n, and then divided by how long or how many years you have already paid, and then you will have the average of the cost for each of the year, and then that will be the O n log n in this case. So that is the analysis of the algorithm, and we just have one more small thing. So that is called a greedy strategy. So a greedy strategy is it's not a single algorithm, but it is a way that we can design many algorithms. And well, the strategy of designing greedy algorithm is that we build the solution piece by piece, and then for each of the step, we only move on to the direction which is the most obvious, and then give us the highest immediate feedback. And then if we always go this way, we are just going through all the local best option. So on the status 1, and then I'm taking the local best option, so I'm going to status 2. And on the status 2, again, I'm taking the local best option, so I'm moving on to status 3. And then if we just move on, and then we are combining a lot of the local best choices, and then we are going to have a global solution. Okay, and then if we step back and take a look on the Kruskal algorithm, so let me go back. So what we did was, well, we started from the lowest, right? and then we start from the lowest, and then we decide if we want to take that or not, and then we move on, and then we try to do the next one, and then we again for the next one we want to decide if we want to pick that or not, and then we always doing this. So when we are doing those steps, are we really having a global vision of what is gonna end eventually? No, we are just for each of the step we only take the local best choices and following very simple rules, right? So we take the 1, we take the 2, we take the 5, and we take the 8, and then so we are just following this set of the rules, and we have no global vision at all. And guess what? We just keep on taking all the local best choices, and then we just combine the local best choices together. And guess what? So eventually we have a minimum spanning tree. This is a minimum spanning tree saying that is a global best solution, right? Okay, so this is the really cool thing about the greedy algorithm. So, well, we don't have a vision of the global picture at all. We're just taking the local best choices step by step, and then when we put all the local best choices together, we have a global optimal solution. So the point is, for the Kruskal algorithm, it is a greedy algorithm. Okay, so the task for you is go back and take a look on the Prim's algorithm and tell me, is Prim's algorithm also a greedy algorithm or not? Okay, well, you are going to see this question in the quiz too, so take a look on the Prim's algorithm definitely. Okay, so that is the last, well, this is the last of the lecture video. So we are finished all the items, all the topics I want to cover in this course. And well, there might be a few more videos. What I'm planning to do is I'm going to make 2 videos explaining the homework 5 and homework 6, and to help you guys prepare for the final exam. And if you have other suggestions on, hey professor, can you do another video explain algorithm X again? Well, shoot me an email and I will see if I have the time to make the video for you guys. Okay? So the next part is the weights of this course. So those are the weights we have seen on day 1 of this class, and now I have already put them into the canvas. So now in the canvas, if you see your total score, that is the total weighted score based on what have already been posted. Okay, so that is not the total weighted score, but that is the total weighted score on the available posted scores. And another thing, another very important thing, I have a favor to ask. Well, go ahead, please go ahead, click on this link and then do the class evaluation. And well, if I have more than 70% of the response rate, I will offer 1% up curve for everyone. So if you have the total weighted score as 89, for example, and 89 is going to be a B plus, right? If you add this 1% up curve, and you will be 90, and then 90 will give you A minus. Okay, so go ahead and try to fill in the class variation, and I will appreciate that.